Okay, so continuum models of elastoplasticity. And I want to distinguish continuum as being pertinent to three-dimensional models. So when I say continuum, really, I'm referring to, three-dimensional theories of elasticity, but now we're introducing this additional component of elastoplastic nonlinear material behavior. But before we dive into some of the details and kind of rationalize how exactly we get there, let's recall what we developed in the previous lecture on the subject of these simple one-dimensional representations of elastoplastic material behavior. So if you remember in the last lecture, we proposed to develop some kind of component-based model, an idealization of elastoplastic material behavior, which we could construct by taking maybe some springs and maybe some kind of frictional sliders, these one-dimensional elements. We could pattern them together in this kind of assembly. And the resulting behavior that we get out of the whole system put together gave us some behaviors that kind of look like what's shown on the figure on the right. So in other words, if we had some assembly of springs and this slider, the slider in general will resist sliding as long as the stress that's being put through that particular slider element, doesn't exceed some critical threshold. It's kind of equivalent to supposing that this slider is kind of like a block sliding on a rigid surface that has some frictional resistance, and it won't slide at all if it doesn't have some critical sliding force applied to it. But past a certain critical force threshold, then it starts to slide. And there were a few different ways that we could construct this model to include different behaviors that exhibited an apparent increase in the resistance to sliding, depending on whether you're choosing to put, let's say, some spring in parallel with this slider, which would result in, an apparent increase in the resistance of this whole assembly to continued sliding of that kind of slider element. And that gave us behavior that I kind of referred to as kinematic hardening. It was kind of equivalent to supposing that you would have, the actual kind of envelope of the kind of so-called elastic range of this representative model, maintaining kind of like a fixed width. The other way that we could increase the apparent, strength of this material as we continue to deform it and permanently kind of slide this element back and forth is by supposing that instead we actually increase the apparent sliding force resistance, which I called the yield stress associated with this element. We could have that actually depend on something called the equivalent plastic strain. It was kind of a measure of how much total permanent deformation or plastic strain has kind of accumulated in this slider element over potentially multiple cycles of deformation. So if we introduce that dependence, then we got slightly different behavior that kind of looked like, rather than the yield stress of the material staying a constant, it kind of like increased over time uniformly. And we called that behavior isotropic hardening. So in any case, we came up with this model. It's relatively simple, but I want to point out that fundamental to the construction of this one-dimensional simplified plasticity model is this idea that the total deformation experienced by this whole assembly of, the springs and this slider put together, that the total strain, in other words, associated with this whole assembly could be broken up into two parts. In particular, the strain that would be put into stretching this particular spring with stiffness E, and the strain that would be put into this whole kind of subassembly that includes the slider. And in general, you could kind of refer to those two different portions of the total strain as the elastic strain, kind of the strain that you would see if the material wasn't exhibiting any kind of active permanent deformation going on. And it corresponds to behavior that would show up in kind of the slope of these stress strain curves, where the slope of that curve is directly proportional to just the Young's modulus of the material. And then the plastic strain is really the portion that corresponds to the permanent deformation that occurs due to the sliding of this kind of slider element. And it's the strain that you would see if you were to try to remove all of the stress that you were applying to this whole assembly and allow this kind of elastic spring to, compress back down to effectively zero elastic strain. you might still see that there's some residual strain built into this assembly that's proportional directly to this plastic strain. So that's kind of the idea. We've posed that we can decompose the strain in this way into an elastic part and a plastic part. And furthermore, we suppose that the actual perceived stress in this whole assembly is just directly proportional to precisely, the stress in either one of these two subassembly elements. Or equivalently, we could just say that the stress applied to this assembly is just directly proportional to the stress in this simple elastic spring. Or in other words, E times the elastic strain. So we could propose then that we have some kind of stress-strain relationship that looks like this. The stress in this whole assembly is just proportional to the stress in either one of these components, but making things simple, just choosing this particular one. All right, so E times the elastic part of the strength. Now, how exactly do we generalize this concept into the case of some kind of multi-axial, kind of three-dimensional constitutive relationship? Well, it actually proceeds along similar lines by proposing that in like fashion to how we tried to decompose the total strain into an elastic and plastic part in this kind of one-dimensional sense, similarly, we can propose to decompose the total strain tensor, that full 3x3 array of strain components. We choose to decompose it into two sub-tensors, if you like, an elastic strain tensor and a plastic strain tensor. And making things simple, assuming relatively small deformations, it's reasonable to assume that you can partition the strain tensor in an additive way into those two subcomponents, the elastic strain tensor and the plastic strain tensor. And the intuition behind exactly what these different measures of strain represents hopefully is somewhat straightforward. But supposing you had some initial configuration of a perfectly square block, let's say in this kind of example, and it's subjected to some total amount of deformation, the total strain, in other words, it's the strain that you would see actually and be able to physically measure if you were to run an experiment and kind of observe how much deformation is occurring. So the total strain is the strain that you actually see, and these other measures of strain are somewhat fictitious. However, if you were to, let's say, deform this chunk of material, originally a square, until it kind of stretched out into this final configuration, and then if you were to remove whatever load you put on this, assembly to kind of let it spring back elastically into ideally its original configuration, if some plastic deformation occurred, if some permanent deformation occurred, what you would see is it wouldn't spring back to this original perfect square configuration. It would spring back to this kind of permanently deformed configuration. And you could measure then what's the resulting permanent strain or plastic strain that occurred in this chunk of material. And it might look something like this, where not only would it, kind of like look like it's stretched out, vertically, it may have also contracted inward. So in general, when we're talking about permanent strains or plastic strains, these deformations, don't just have an axial component, they also have kind of some lateral components of strain. So we'll discuss a little bit about that in a moment. And then whatever, differs between these two measures of strain, the total strain and the plastic strain, that's the portion of strain, the elastic strain, that actually accounts for how much stress will develop in the material. So really, it's kind of like you're saying, treat the new kind of reference configuration of the material, or in other words, the configuration of the material in which a state of zero stress will occur. It's kind of like you're saying, this is the new kind of zero stress configuration of the material, this configuration in which you have plastic strains kind of looking like this, which have permanently changed the, like that zero stress configuration of the material. Okay, so we've decomposed the strain tensor now into an elastic part and a plastic part, and we've supposed now that we can construct, similarly as we did in the one-dimensional case, a constitutive model that says that the stress internal to the material doesn't just depend on the total strain in the material. In fact, it is just proportional to only the elastic part of the strain. So equivalently, you could say, take the total strain, the thing that you can physically observe, subtract off the plastic strain, and you'll get basically just the elastic part of the total strain. Okay, so in likeness to the way that we kind of developed our regular isotropic elasticity models, we can suppose that there's some linear relationship between stress and strain, adopting the same conventions that we had previously by supposing that maybe we can define this rank 4 constitutive tensor. Equivalently, if you want to arrange the stress and strain tensors into the format of, vectors that contain 6 independent components each, then we could choose to instead format this, rank 4 tensor into the format of a nice, just simple 6x6 matrix. So either way you do it, the idea is still the same, that you can still use our original elastic definition of the relationship between stress and strain, but now the only thing that we've really changed is that we have to plug in the elastic strain rather than the total strain, and where these things are now interpreted as tensors, not just uniaxial components of strain. However, it is rather convenient and nice to notice that if we were to look at the particular case of a uniaxial state of stress, we could still come back and find that the relationship between, elastic axial strain and the actual kind of axial component of stress that would result in that uniaxial state of stress actually kind of follows directly from this expression. So if you assume that the other components of, strain are potentially non-zero, but if you suppose that the other components of stress apart from sigma xx are equal to 0, then you actually get something that depends directly on just, the elastic strain, or the elastic modulus rather. So that's kind of nice. We get agreement with the uniaxial kind of simple one-dimensional idealization that we developed previously. Okay, and again here it says that, in the one-dimensional case, it's just proportional to total strain minus the plastic strain. Okay, so that's the simple case of coming up with this multiaxial plasticity stress-strain relationship. And I also want to point out that the strain tensor, or rather the plastic strain tensor, again, itself could contain a full array of different values that might have, axial components of plastic strain as well as shear components of plastic strain that could show up. However, I do want to point out that there are some physical constraints that are typically imposed on the nature of this plastic strain tensor when we go into this context of multiaxial plasticity. In general, it's assumed for most materials, and more specifically for most metals, which typically undergo plasticity and permanent deformations, it's usually the case, and you can show this, you can rationalize it on the basis of different, investigations of what's actually happening at the material microscale. But for metals in general, whenever you have plasticity or permanent deformation of the material, what's happening is that it's not so much that the material is permanently elongating in just one direction. Really, at the microscale, it's kind of like the atoms in the packing configuration of the material are just moving around and kind of squishing, but without changing the apparent volume of the material. So in other words, when we have plasticity, it effectively corresponds to a purely distortional deformation, which is volume preserving. So that's an important observation. It basically says that if we're trying to represent these permanent plastic deformations in the material through this description of a plastic strain tensor, it effectively means that in order to ensure that these plastic deformations are volume preserving, then we have to insist that this plastic strain tensor has to exhibit 0 apparent, volumetric strain, which is another way to say that if we were to measure the dilatational portion of the total strain in this strain tensor, we would find that the dilatational part of this strain tensor is equal to 0. So if you were to sum up the diagonal entries, epsilon xx, yy, and zz in this plastic strain tensor, they would actually all sum up to 0, which is indicative of a state of strain that preserves the total volume of some original chunk of material. So if you had an original cube of material that had a unit volume, and you subjected it to this permanent, plastic strain deformation, you'd find that the volume of the deformed kind of chunk of material actually maintains that same unit volume. Now, again, I want to point out that this is kind of a limiting condition that applies only in the context of relatively small deformations. That's kind of a limiting assumption, but it's one thing that I want to point out because you can kind of get yourself into trouble if you have relatively large plastic strains occurring, it isn't exactly the case that this is the constraint on the total volume preserving nature of the plastic deformations. That's more of a subtlety, but at least for the present context, let's assume that this is true. Okay, so we've said plastic strains, actually have to be volume preserving, so they have to satisfy this additional constraint. And how exactly is that useful? Well, it's important to point out that if we're supposing that our material behavior is effectively the same as what we'd previously developed for the case of isotropic elasticity, then recall in the case of isotropic elasticity, we could actually come up with our relationships between stress and strain by proposing that there's a way to decompose that constitutive relationship into two parts. If I had some total strain, in this case, actually just the elastic strain in the material, I can actually separate out that strain in the material into two parts. One part that's representative of the volumetric strain or the dilatational strain that occurs in the material. That corresponds to basically full isotropic expansion of the material or isotropic compression in all different directions. And also the deviatoric strain or the distortional strain in the material that kind of looks like pure shearing types of deformations or any type of deformation that is inherently volume preserving, going back to that same concept. So if we separate out the elastic strain into a part which is dilatational, as well as a part that is purely deviatoric, then we could actually come up with direct relationships, separable relationships between the dilatational volumetric strain in the material and the resulting hydrostatic pressure, kind of like the average state of pressure in the material. Similarly, we could come up with a relationship between the deviatoric strain in the material and the corresponding deviatoric stress in the material. And again, the pressure in the material is kind of like the pressure that you would see in some kind of fluid. It's basically a uniform pressure that acts with a uniform magnitude of pressure, P, on all different faces of some cube, whereas the deviatoric stress corresponds to a state of pure shear stress acting on some cube of material, although it might not necessarily look like it's shear stresses that act on all different faces of the cube. You'd have to choose a particular configuration to actually get it to look like that, but never mind that. The idea is we can come up with these separable relationships to come up with a description of the total stress that results in this chunk of material that can be separated in this way into a dilatational part and a deviatoric part. Now, going back to the idea that if we're expressing our description of the elastic strain as really the total strain minus this plastic strain expressed as tensors, then I want to point out by enforcing the condition that the plastic strain tensor has to be descriptive of a purely volume preserving deformation, then we actually find that the contribution of the plastic strain to the total dilatational strain of the material is zero. It just goes away, which suggests that the dilatational portion of the material's behavior overall really only depends on the total strain in the material. It's only the deviatoric portion of the deformation that contributes to changes in the relative deviatoric stress that results. So in other words, regardless of what's happening in the material, regardless of whether it's being subjected to plasticity, the apparent average stress or the internal state of uniform kind of pressure in the material doesn't change, even as it's kind of undergoing plastic deformations. The only thing that changes is the deviatoric stress. That's the thing that's affected by plastic deformations. So in effect, we shift the deviatoric strain in the material by the corresponding plastic strain, which is itself by definition a purely deviatoric tensor. It has a trace that's equal to zero. We find that we can describe this deviatoric stress tensor S just purely through this simple relationship that depends on G, the shear modulus. So quite simple, quite nice. And how can we make use of this? Why is this useful? Well, I want to point out one other thing before I actually demonstrate how this decomposition is useful. And to explain this, we have to maybe take a little bit of a detour. We have to go back to maybe your mechanics of materials courses or maybe something that's rolling around in your memory at some point. We have to talk about principal stresses. Now, raise your hand if you recall this concept of principal stresses. Maybe we can take a shortcut. some of you recall. Anyone who's maybe needs a little bit of a refresher on the concept of principal stresses, maybe at least a couple of you perhaps. Okay, so we'll kind of dive into this. So the main idea that I want to present, again, a little bit of a detour, but stay with me. The idea is that suppose I had some block that I can express, the stresses that act on different faces of this block using different components of the total stress tensor that this block of material would see. So I can propose, to choose some coordinate system, with X, Y, and Z axes. I can choose to align this block of material such that its edges align with these kind of like major coordinate directions. And I can define the stress tensor's components relative to this particular coordinate frame, the global coordinate frame of whatever problem I've chosen to analyze. And I can take all these different components of stress, the force per unit of area acting on different faces and in different directions, and put them into the format of this 3x3 tensor. That was how we defined the stress tensor to begin with. Now, I want to point out something interesting, which is if I had this same state of stress, I didn't change how I chose to load this, block of material. The only thing that I chose to do was instead do some kind of change of coordinate frame for the problem that I was looking at. So maintain whatever same kinds of loads I'm putting on this problem, but just change the definition of the coordinate frame into some other rotated coordinate system, which I'll denote with these hatted symbols. So X hat, Y hat, and Z hat are my new coordinate axes in this rotated, transformed coordinate system. And looking at the same exact state of stress, just defined relative to this new rotated coordinate system, it happens that for any possible state of stress that I could choose to define, regardless of how I've chosen these different components of the stress tensor and regardless of how I've defined the loads, for any such possible stress tensor, there is always some coordinate system which I can choose to rotate my description of the stress tensor into, which actually results in a state of stress that has components that act strictly normal to the faces of this rotated cube. And that's pretty fascinating. It basically means that it's always possible to express some generic state of stress that might have shear components of stress in it into this format, which looks like there are no components of shear stress acting in it. Now, that doesn't necessarily mean that there is no shearing going on. Certainly, it just depends on how you've chosen to define your coordinate system. But the main idea is that if I have some generic representation of a stress tensor with 6 different components, I can choose to just define a special coordinate system corresponding to the so-called principal coordinate frame, in which I can choose to define the state of stress just in terms of these 3 normal stresses acting on the faces of the cube that are aligned with these principal coordinate directions. And these 3 components of stress are themselves referred to as the principal stresses associated with this particular state of stress. So that's pretty nice. It basically means if I don't want to have to represent all these different components of stress, I can just choose to, define some different coordinate system, one that happens to align with the principal directions of this particular, loading on the block of material. And I can now express the state of stress just in terms of these 3 principal stresses. And obviously, analyzing principal stresses has general utility if you want to know, what's the maximum principal stress or the maximum tensile stress, on any possible oriented plane in some chunk of material. That's useful for analysis and design purposes, but it's also useful for visualization purposes of states of stress as expressed through these principal stresses. So the idea is, if I can represent any state of stress in terms of not its 6 independent components of, normal stresses and shear stresses, if I can just boil it down into a representation in terms of the principal stresses alone, then I can represent that state of stress in terms of just 3 values. And if I like, I can kind of take an interesting visualization-based approach to representing these states of stress by supposing I can arrange those 3 principal stresses into the format of a vector. And in doing so, I can represent any state of stress expressed through the principal stresses in this so-called principal stress space. It's analogous to a three-dimensional physical space, as you might interpret as, as you interpret as the space that we live in day to day. But in fact, it's basically just a three-dimensional coordinate system where, the actual dimensions of these axes correspond precisely to the different values of the principal stresses, sigma 1, sigma 2, and sigma 3. So if I wanted to represent a particular state of stress within this principal stress, coordinate system, I can basically describe it as some point that exists somewhere in this three-dimensional space. Kind of a fun idea. Now, it's also useful, and I'll point out that there's a particular perspective that you can take when looking at this principal stress space that is sometimes called the pi plane. It is, in other words, the perspective that you would take if you happen to be looking down at this kind of coordinate set of axes, at least from this perspective, kind of looking at it as though, you could somehow visualize these three different axes as pointing in different directions that differ by, I think this angle is maybe like 120 degrees or something like that. So different perspectives, nonetheless, of the same coordinate system. All right, so that's the whole idea behind principal stresses and visualizing principal states of stress within this principal stress space. Now, why is this useful, and how does it relate back to this idea of plasticity as we've previously discussed? Well, really, what we want to come up with is some description of a criterion when some chunk of material will meet some critical threshold for an internal state of stress, and beyond that critical threshold of stress, we expect that plasticity or permanent deformation will start to occur. Now, the question is, how exactly do we construct that criterion? How do we specify when will the stress exceed that limit? The problem is, if we have stress described through this tensor, this kind of like collection of 6 different components of stress, it's not exactly clear how we should define a criterion for when the material will start to yield, or when will it deform plastically. We have to somehow come up with a description of a yield criterion that is independent of the choice of coordinate frame that we've chosen for our problem. And ideally, in doing so, we should be able to come up with a criterion that's expressible purely in terms of just the principal stresses in the material. So that's kind of the goal. Now, the idea here is that we can define actually some interesting measures of stress as defined within this principal coordinate system. So suppose I had some total state of stress. Again, I could represent that state of stress in terms of the principal stresses as some point in principal stress space. That's what I'll call this kind of vector, if you like, sigma, consisting of those 3 principal stress components. Now, remember, any stress tensor that I want to define can also itself be decomposed into 2 parts. A part that involves just pure hydrostatic pressure, and a part that corresponds to pure distortional or shearing stress in the material. So P, the pressure or the average stress, and S, the deviatoric stress. Now, when represented within this principal stress space, it's interesting, you can actually show that the component of the pressure in this material actually corresponds to some new vector that happens to be aligned with some axis that is equidistant from each of the 3 different principal axes in this stress space. So it's always oriented basically in a direction that, at least from this perspective, looks like it's pointing straight out of the page. That's the special kind of property of this pi plane perspective on this kind of principal stress coordinate system. It basically means that this so-called hydrostatic axis, if the axis aligned with pure, pressure states of stress in the material, that axis happens to be, pointing directly out of the page in the pi plane. Now, the other portion of the stress, the deviatoric portion of the stress, acts in a direction which is in fact perpendicular to this kind of hydrostatic axis. Or in other words, if we were to look at this kind of deviatoric part of the stress, S, from the perspective of the pi plane, that's the only thing that we would see. It's basically the kind of projected length, in other words, of the stress tensor projected onto this kind of like 2-dimensional plane viewed from this special perspective. So that's kind of the advantage of looking at things from this pi plane point of view. But the idea is, now if we look at this perspective, we can see that the deviatoric stress looks like a vector that's in this kind of projected two-dimensional coordinate system. And from within this coordinate system, we can also notice that, this kind of apparent length of this vector, the deviatoric stress vector, if you like, that the apparent length of that vector, we can actually measure that if we want. We could measure that by basically taking what's the norm of this vector defined in this, principal stress space. And we can define that norm of that vector as being something that's sometimes referred to as the von Mises stress. It is specifically the apparent length of the deviatoric stress vector defined relative to this projected pi plane in principal stress space. Getting kind of crazy, getting kind of weird, but the idea is it doesn't matter exactly where this kind of vector is pointing. We can always kind of measure its relative length. And we can define it in terms of the principal stresses defined in this principal stress coordinate system, or we can actually equivalently define it directly as basically taking some measure of the length or magnitude of our deviatoric stress tensor. And it looks kind of like this. So the von Mises stress is effectively a measure of the magnitude of shear stress in the material. It's also related to another measure of shear stress, sometimes called the octahedral shear stress, if you've happened to have heard of that. But the idea is that the von Mises measure of stress includes no dependence on pressure in the material. It's purely a measure of deviatoric or shear stress. So the way to interpret von Mises stress is that it's really kind of a measure of the total magnitude of shear in the material. So it stands to reason that if we know we have materials that exhibit elastoplastic behavior, but they only influence the deviatoric or shearing part of the total stress in the material. And if we further have a way of measuring what's this kind of total magnitude of shear stress in the material through this single number, the von Mises stress characterizes a value of shear stress that is always, just a single scalar, a single number, and it's always greater than or equal to 0. Those are some interesting and nice properties. Now, what this means is that we can choose to define this von Mises stress measure as the particular measure of stress that we will use to come up with some criterion for when plasticity will occur. And that's exactly how conventional models of elastoplasticity in the context of these continuum formulations are constructed. They suppose that there is some constraint imposed directly on this von Mises stress such that we require the von Mises stress in some chunk of material that's being subjected to loads has to be constrained to be less than or equal to some yield stress, the maximum stress in the material that can be sustained before plasticity starts to occur. Now, the idea is that if the state of stress in the material gives me some measure of von Mises stress that is somehow less than that yield stress, as long as I'm less than the yield stress, then I assume that the material behaves purely elastically. It doesn't undergo any plastic deformations. Now, you can imagine that states of stress that satisfy this condition effectively look like points that lie within some kind of cylinder defined in this principal stress space. And in the pi plane, it just looks like a circle, which is kind of nice. So the idea is, if I'm looking at things with respect to the pi plane, and I'm looking at the state of stress in the material as some point in this principal stress space, as long as that state of stress described by some point in this kind of pi plane, as long as it's inside of this circle, I know that I'm basically, exhibiting purely elastic material behavior. No plasticity happens. But if I somehow increase the state of stress in the material such that it gets bigger and bigger and bigger, and the von Mises stress starts to get bigger and bigger, then I start to approach this kind of surface of this yield constraint that tells me that eventually, once I hit that surface, that's when plasticity will start to occur. So it's kind of an interesting concept that you can visualize this interpretation of the yield constraint in this fashion as kind of describing almost a surface in three-dimensional kind of stress space. And sometimes this is exactly how this yield constraint is described. It's sometimes referred to as a yield surface. It's basically some surface that describes, some kind of three-dimensional, like physical interpretation of a surface in this principal stress space that corresponds to the criterion for yielding. So anytime you're inside the yield surface, inside of this cylinder, in other words, I assume I have elastic behavior. Anytime I try to go outside of the yield surface, that's when I have plasticity. And that's kind of an interesting phenomenon, right? It basically says I can define my criterion through this kind of nice relationship. But the question is, how does this ultimately influence, plasticity? How exactly do I know if plasticity is going to occur? Well, how exactly does that influence the apparent permanent deformation that occurs in the material? That's the other thing we need to kind of connect together. Ultimately, when plasticity occurs, remember back to that one-dimensional idealized model. In that one-dimensional idealized model, we had a spring in series with this kind of slider. And we suppose that the elastic strain in the material was the only part of the strain that actually contributed to stretching of this spring and corresponded to the resulting stress in the material. However, the permanent deformation that occurs, the plastic strain in the material, evolves when I reach some kind of critical threshold for the yield stress. And at least in this one-dimensional case, it basically means that this plastic strain will start to increase, let's say, if I start to increase the amount of applied stress on this whole assembly. And at that point, once I start to have yielding, the plastic strain will start to increase if I'm putting this thing in tension, or if I'm putting into compression, the plastic strain will kind of start to decrease. It'll diminish in the opposite direction. Somehow we want to generalize that same kind of concept to come up with some way of updating the apparent plastic strain or the permanent slip that's happening internal to the material based on, exceeding some criterion for when plasticity occurs. And without kind of belaboring the details too much, the idea boils down to supposing that there's a way to define the apparent rate at which plastic strain occurs, and more specifically, not just defining what's the rate at which plastic strain occurs, we also have to define how exactly is the plastic strain evolving. In the one-dimensional case, we had to resolve if we were kind of stretching the material this way, was the plastic strain increasing or was it decreasing under compressive loading? We had to distinguish, in other words, what's the apparent direction in which plastic strain will start to flow or increase. And the basic idea is we need to come up with a similar such flow rule or some kind of description of how the plastic strain should increase or decrease depending on whether we're putting this thing into a state of tension or compression. And the way that we do this in the case of multi-axial plasticity models is to define some kind of flow rule that tells us how the plastic strain should evolve, at what rate, and also in what direction. It so happens that typical models of elastoplasticity, especially for things like metals and so forth, the flow rule is defined such that the direction of plastic flow, sometimes described through this kind of vector n described in principal stress space, but the direction of plastic flow or increase in plastic strain actually is directly aligned with the applied deviatoric stress. So that's kind of the interesting thing. If I have some deviatoric state of stress in the material, let's say if I'm putting the piece of material into a state of tension, then the plastic strain has to increase in that same kind of direction of loading, if you like. So if I'm putting it in tension, then I expect plastic strain is going to increase kind of, corresponding to elongation of the material. If I'm kind of putting the material in compression, kind of reversing the direction of the loads, then we expect the plastic strain to kind of decrease in the same direction. So you can describe this direction as basically characterizing the apparent normal to this yield surface in principal stress space. It's kind of a fun idea that we can kind of still use this same visualized representation of the yield surface to describe the direction of plastic strain evolution as just corresponding to the normal to the surface, which in the case of the pi-plane is just some vector that lies in this two-dimensional space that is always pointing directly outward from the center of this kind of yield circle, if you like. All right, so plastic strain will always evolve in a direction, in other words, that corresponds to the kind of direction of the applied deviatoric stress. Okay, and you can also associate with this kind of direction of loading a corresponding equivalent rate at which plastic strain will occur, and that corresponding rate is directly proportional to the equivalent plastic strain. Now, I defined last time, the equivalent plastic strain was kind of like the sum up of all the increments of plastic strain that would happen in the material taken with an absolute value. So equivalent plastic strain is a measure of plastic strain that corresponds to a single scalar value. It's just one number rather than a whole tensor of values. So the equivalent plastic strain is a measure of plastic strain that's always increasing, a single scalar value, and it kind of gives us a measure of how much total plasticity has this chunk of material experienced over many cycles of loading. And if it's always increasing, then you can kind of keep track of, how much plastic strain is accumulated, regardless of the direction of the loading. So it's kind of a direction independent measure of plastic strain, and it's always increasing. Okay. So that's equivalent plastic strain, some of the ideas behind plastic strain evolution through this flow rule concept. And the other kinds of concepts that I want to bring back into the picture related to how exactly we represented things like apparent increases in hardening behavior of the material as we subjected it to plastic deformations. Remember, in the one-dimensional case, we had two different ways that we could include dependence of that yield constraint equation on increases in plastic strain. There was that description of isotropic hardening, which was kind of like saying that the yield stress itself depends on how much plastic strain has accumulated. And one way to include that dependence is supposing that the yield stress itself depends not on the total strain, or rather not on the total plastic strain, but on the equivalent plastic strain, that kind of variable that is always increasing and is basically just a single scalar number. And if we include this dependence, if we suppose that the yield stress depends strictly on the equivalent plastic strain, then it kind of looks like our yield surface, originally some kind of cylinder in principal stress space, with increases in equivalent plastic strain, it'll look like our yield surface is getting bigger. It's expanding. And kind of to connect the terminology together, it's expanding isotropically. It's expanding the same amount in all different directions, at least within the pi plane. So that's kind of the idea behind isotropic hardening. Isotropic hardening describes an increase in this yield stress in the material that corresponds directly to increases in the equivalent plastic strain in the material. Now, that's not the only way that we could kind of adjust our yield constraint. We could also include kinematic hardening, which is a little bit different. Rather than supposing that the yield surface is getting bigger, corresponding to some residual slope as we would have in some kind of strain hardening material, this being kind of representative of hardening behavior with a tangent modulus that's greater than 0. Another way that we could represent hardening behavior is by supposing that, well, let's not necessarily increase the radius of this yield surface. Let's actually just shift it, move it in principal stress space by some amount, which is sometimes referred to as the back stress. It's kind of like the residual stress in the material that occurs due to plasticity. And it effectively measures the amount by which the center of the yield surface has been shifted without actually augmenting the diameter or the radius of the whole yield surface itself. And to actually make this representative of how we would evaluate our yield criterion, we actually have to shift or kind of subtract off this back stress from the deviatoric stress when we actually compute this measure of effective stress, or von Mises stress, if you like. So the back stress tensor, if you are assuming a purely linear relationship between the back stress and the corresponding plastic strain in the material, then you'll get this so-called linear kinematic hardening rule, which basically says that now we can introduce some dependence of our yield constraint directly on the total accumulated plastic strain. And the interesting thing about this is that if we were to cycle the material through some kind of like loading history that looks like loaded in tension, loaded in compression, if we continue to load the material plastically, it'll kind of look like we end up shifting the yield surface maybe this way when we load it in tension. And then if we reverse the direction of loading, it'll shift back. So it's constantly moving around to accommodate, active plastic deformations that might be occurring. But the shifting of the yield surface basically means that, if I shifted the yield surface this way, and then I reverse the direction of loading, I might find that actually now I might encounter yielding at a much earlier time than if I tried to load directly this piece of material in, let's say, compression or something like that. So shifting of the yield surface sometimes is more representative of the material behaviors that you're interested in modeling. But ultimately, typical materials might exhibit some combination of both of these things. Some isotropic hardening, some kind of increase in the diameter of the yield surface, and maybe some kinematic hardening, some kind of shifting of the yield surface in principal stress space. So both of those things are possible. All right, some other interesting details that I'll throw at you are pressure-dependent materials. And this is more typical of materials like granular media, soils, to a certain extent, concrete even. Certain materials like that will also undergo permanent deformations and plasticity. However, they will undergo plasticity at different times depending on how much pressure is in the material. So you can do this experiment with some kind of confined sample of sand or some other kind of granular material like that. If you don't impose any kind of uniform kind of compression on the material, and you try to subject it to some shearing deformations, what you'll find is that it'll end up shearing at a much earlier time if you have no pressure imposed on that sample of material, as compared if you were to take that same sample and subject it to a ton of compression. It's kind of like you take all the grains of sand, you compress them together and make it really difficult for those grains of sand to slide past each other. Effectively, what that means is that the apparent yield stress of that kind of sample of sand will increase if the apparent state of pressure in the material, that uniform compression, is increased. So with larger and larger values of pressurization of the material or confinement, I can effectively increase the apparent yield stress in the material. And how that actually appears in this principal stress space is I can define a yield surface that reflects that dependence of the yield stress on the state of pressure in the material, like so. And it looks kind of like a conic section defined in this principal stress space, rather than a cylinder, which exhibits absolutely no dependence on pressure. Now I can introduce this pressure dependence and it looks like, a cone, essentially. There are other interesting ways that you can introduce pressure dependence into these types of materials. Rather than a cone, you could also have some kind of ellipsoid defined in principal stress space that says that maybe there's some kind of limits in both tension and compression on the amount of pressure that the material can sustain before it actually undergoes some permanent deformation. So this particular dependence on pressure and this kind of conic representation of the yield surface, this yield criterion is sometimes called the Drucker-Prager yield surface. So a particular instance of this conic dependence on pressure. And again, commonly used for soils and other types of granular media. Now, the last thing that I'll point out to connect all these dots together is to say that all of this that we've developed, supposing that we can define our kind of criterion for yielding in this kind of multi-axial setting, it turns out that if you were to go back and say, well, what if we were to just load this chunk of material uniaxially? Suppose that, we're loading the material in such a way that sigma 2 and sigma 3, those are just equal to 0. So effectively, we're just loading the material just along this one principal coordinate axis, corresponding, let's say, to the XX component of stress, the only non-zero component of stress in the material. It turns out that at least if you kind of go through the task of actually reformulating how exactly the von Mises stress would come about in this expression, you'd actually find that the von Mises stress is nothing more than just taking the absolute value or the magnitude of that axial component of stress. And in this kind of projected diagram, you can kind of see that the apparent, bounds of this yield surface, now in this kind of axial strain versus axial stress diagram, the bounds of this yield surface directly correspond to these kind of like dashed line limits of a typical kind of like two-dimensional stress strain plot. So you can imagine if, let's say, this yield surface is expanding due to isotropic kind of hardening behavior, then these two limit lines are going to kind of get further away from each other. However, if I have shifting of the yield surface, kinematic hardening, then it's going to look like the whole kind of domain of behavior in which elastic behavior will occur will shift up or down depending on the direction of loading that I'm putting on this kind of whole thing. Regardless, as long as I'm inside of this cylinder, or in other words, as long as I'm inside of this kind of intermediate region between these two dashed lines, I'll have purely elastic behavior. And if I try to go outside of these bounds, that's when I have to actually evolve plastic strength. That's when plasticity occurs. Okay, so kind of an interesting thing, but the nice thing is we can reconcile everything and connect it back to these simple one-dimensional idealizations of plasticity. So it all comes together. Now, we won't have time to kind of finalize some of the ideas of how exactly do we implement these concepts in an algorithmic sense. We might have to reserve discussion of that for next time. But at least this hopefully gives you a sense of how exactly we could go from this to that, basically the three-dimensional models of plasticity. But the main idea still that I want to drill home is that as long as you have a reasonable understanding of what's going on just in this one-dimensional case, it still gives you a fairly good intuition and understanding of what's happening in the multi-axial case. The same principles apply, and a lot of the basic ideas are the same in coming up with a yield criterion and coming up with a flow rule and coming up with some kind of decomposition of the strain into elastic and plastic parts. All those things are the same. They just become a little bit more complicated and require working with tensor notation and potentially also kind of looking at things in this principal stress kind of context. All right, that's all we have for today. I'll see you on Monday.